Do we have slides for this?
Yes, thank you. Thank you for asking, Glenn. I will post the link now. And I close that. I will put them in lessons. Alrighty then. Here we go. Logic and truth tables. My high-res slides here. Alright, so Boolean algebra, or Boolean logic, is a branch of mathematics that involves the binary system, true and false values. So a lot of times you'll see true denoted as T or 1, and false denoted as F or 0. In some languages where they just have to be different, they'll switch it. True is 0 and false is 1. But almost always, true is 1 and false is 0. Okay. So we use Boolean algebra to break down complex problems or statements into digestible logical formulas, and that's really all that computer programming is. That's it. It's all ones and zeros. It's all trues and falses. So let's talk about some Boolean operators. So a unary operator is an operator on a single value. And examples of that are the identity operator, so true is true and false is false. And the negation operator, which just negates whatever it is the value is. So not true is false and not false is true. And then we have binary operators, and there's a number of these, and I should add one to here. Actually, I did add it in the other slides, which is, I'm going to move it one up, NAND. So there's and we're all pretty familiar with these already, okay? So it's really a kind of a review in some ways, but it just puts into really clear terms some of the things that we're doing already with conditional statements and so forth, loop terminators. So some binary operations are AND. So AND is true when both propositions are true. And in AND, NAND, or not AND, is the opposite of that. So it's the negation of AND. OR is true when at least one of the two propositions are true. They can both be true, but as long as one of them is true, then the result of an OR is true. And NOR is the negation of that. So it's the opposite. Exclusive OR, XOR, is exclusive OR, and it's true when exactly one of the two propositions is true. So if they're both true, exclusive OR is not true, it's false. If they're both false, it's false. So exactly one must be true. One or the other, but not both. So regular OR is also called an inclusive OR. And then there's exclusive OR, which means only one or the other, but not both.
No.
Yes?
What about, for XOR, what about when you have three propositions?
You take them two at a time. So with any of these operations, these Boolean operations, you always consider two at a time. So you'll follow an order of operations to figure out which two to consider first. So if there are parentheses, for example, you would do what's in the parentheses first or in closing brackets. And then it's going to be, it's different in different languages. So generally, though, AND is considered before OR. All right? But you always compare two things at a time. And you get a result of that, and then you compare it with the next thing. And you get the result of that, and you compare it with the next thing. There's another kind of operator called a conditional operator, and these are if-then type operators. Okay, so we see this in programming, and there are two different kinds. There's an implication, which if P is true, then Q is true. So P is true implies that Q is true. And then there's one called equality, which is Q is true if and only if P is true. It's also called a biconditional. We're going to look at these in some more detail, okay? So this slide is just sort of a summary of the different types of Boolean operators that you'll come across and the ones that we'll talk about. Let's look at some symbols, because you'll see these symbols in these slides, and then you'll also see them, you know, possibly in text or various places. You'll see letters used to represent propositions. So I'm going to use P and Q in this set of slides. And that just means two statements that we're performing Boolean operations on. Okay? And then there's symbols for not, and these aren't the only symbols for these things. You'll see different symbols in different contexts. But these are the ones that I'm going to use in these slides. Okay? And they're ones that you're likely to see out in the wild too. So there's a not symbol. The and is, I remember that one's and because it kind of looks like an A. And then not and, one way that's represented is just putting a bar over the top of that caret symbol. Or is the opposite. So it's, you can either remember it's the one that's not and, or you can remember it's like union. If you're familiar with set notation, the union symbol's a U, and that is equivalent to what we have with an or. So, and if that doesn't make any sense to you, then don't remember it that way. Just remember and's the one that looks like an A, and or is the opposite one. Okay. Not or, again, is that same symbol but with a line over the top. One way that it's represented. You might see it represented other ways. Exclusive or, one way you'll see it represented is a circle with a cross in it. And implication is an equal sign with an arrow, and equality is like the spaceship operator. It has the less than, equal sign, greater than. That is a symbol used to denote equality. So this is just to help you with what you see on the slides. All right, so we often use truth tables to work out the results and to understand Boolean operations. So you've seen truth tables before, probably. Have you guys seen truth tables before? I think we did it a little bit at one point. So again, here I'm using P to represent the statement that's either true or false. Okay, so P represents a statement that is either true or false. And the identity operator is just P is true, then it's true, and if P is false, then it's false. The negation operator is the opposite. So if P is true, then not P is false, and if P is false, then not P is true. So that's hopefully pretty straightforward. So let's look at some of the binary operators. So and for each of these I'm going to show you a truth table, and then I'm going to show you what it looks like in a Venn diagram. So hopefully between the two it makes some sense. So in the Venn diagrams, what is in the circle with the P in it is where P is true. So P is true inside of this circle, and Q is true inside of this circle. Outside of this circle, P is false, and outside of this circle, Q is false. Okay? So for and, if you look at the Venn diagram, it's where they overlap. It's where P is true and Q is true. Where we both have both P and Q, then and is true. In the truth table, we can see it represented that there's only a truth for and when both P and Q are true. In every other case, P and Q is false. Does that make sense? Stop me at any point, okay, if it gets confusing or you have questions. Now, not and is the opposite. Okay? So in the Venn diagrams, it's, you know, the not of an operator is going to give you everything else. Okay? Whatever wasn't red in the other picture is red in this picture. So if we look at the truth table, we have the opposite case. So not and is only false where both values are true, and in every other case, not and is true. So it really is the negation. Whenever I do negations, I like to actually put just an extra column in my truth table So I would take the and case, and then I would just negate it. So I would take this third column, I'd make another column here that shows the negation. So if it's true there, then it's false in the negation. Okay? Or is true when either or both is true. So this is what or looks like in a Venn diagram. Everywhere that either P or Q is true, then or is true. And it's only where both are false that or is false. And similarly, not or is the opposite of that. So if we took the third column in the or truth table for P and P or Q, then we would just take the opposite for the negation. So wherever P or Q is true, it's going to be false for not or. So it's only true when both values are false. Exclusive or is true where P is true or Q is true, but not where both are true. Okay? So if they're both false, it's still false, just like or. And if one of them is true, it's true, just like or. But if they're both true, it's false in exclusive or. Okay? All right. So those are the binary operators. Any questions about the binary operators? All right. So let's talk about implication. Implication's a bit tricky. It's really confusing because implication and equality are really similar. But the difference is that just because P implies Q doesn't mean that Q implies P. Okay? So what that means is that if P is true implies Q is true, okay, then any time that P is true, Q must also be true. All right? And if that's not the case, then the implication is false. So anytime that P is true, but Q is false, means that this implication, P implies Q, is not holding up. That will evaluate to false. All right? If P is true and Q is also true, the implication holds up, and it's true. If P is false, it doesn't matter what Q is. It doesn't mean anything. The only thing the implication tells us is that P is true, Q must also be true. All right? If P is true, Q must also be true. And if that's not the case, then this implication does not hold up. It's false. So another way to look at it is, for some people it's helpful. For other people it'll be like, how is that helpful? For some people it's helpful to think of it as not P or Q. Okay? Not P or Q for the purposes of filling in a truth table. So that's what I've shown here. You have P and Q, not P. I take by taking the negation of P. So where P is true, not P is false. And where P is false, not P is true. And then I OR that with Q. So then I'm ORing these two values. So true or false is true, false or false is false, true or true is true, and false or true is true. Okay. Now for some people that helps, and for other people you'd be like, that doesn't help me at all. Why is that helpful? Okay. All right. So any questions about that? I think for me the real crux of it is that if we are stating an implication, if we're saying P implies Q, in order for that to hold up, in other words, in order for that implication to be true, if P is true, Q must also be true. Okay? And that's all that matters.
Like what I said earlier with the thing of, when I first learned this stuff to help me was that if you think about something like a statement, like if I'm here, I drove here, right? That does not mean that if I drove, I'm necessarily here.
Right.
Does that make sense?
Yes. Yeah. Or like if I'm here, my car's working.
Yeah.
Yeah, if I'm here, my car is working, because the only way I get here is by car. So if I'm here, my car is working. But that doesn't mean that if my car is working, I'm here. Well, if we're saying the implication is true, that if I'm here, my car is working, I'm stating that as a fact. If I'm here, my car is working. So I'm basically saying that if I'm here, I've driven here, my car is working. I only get here by my own car, driving myself here. So if that were true, and I'm here, it implies that my car's working. Okay?
I don't think no, sorry, like, if I'm, oh no, I get it. You get it.
Yeah.
You're just
You're just being
being
difficult? Okay.
He's just wasting our time.
All right. All right. Now, the equality operator is a biconditional operator. So it's sort of saying like P implies Q and Q implies P. Okay? So if P is false, that means that Q is false for this equality operator to be true. And if P is true, then Q is true in order for this equality operation to hold up. All right? So, and it also means that if P is false, Q must be false. So they're either both true or they're both false, but they can't be different from each other. All right? That's what the equality operator means. So Q is true if and only if P is true. And P is true if and only if Q is true. Okay? So those are tricky ones. The implies and equality operators come into play with if statements. All right? And the binary operators come into place when we're combining propositions in an if statement, in a conditional statement, when we're checking multiple things. This is true. If this is true and this is true, then do this. Or if this is true or this is true, then do this. Okay, so that's where we use binary Boolean operations, is when we have multiple propositions in an if statement. And otherwise, if statements are generally implications. Okay, so we're going to look at some examples shortly, but first we're going to look at bitwise logical operations, because this is another thing that we do. Bitwise logical operations sounds a lot scarier than it is. We can combine binary values of the same length with bitwise logical operations. So if we have two binary numbers that are the same length, then we can just consider each position individually and perform some operation, one of the binary operations. Yes?
We're not talking about numbers, we're talking about true and false.
True and false, because binary numbers represent true and false in computing. That's what we use it for. Yes. So let's look at some examples of this. So here's an example. If we have the number, I have the number 110011. That's this number. And then I have the number 101100. That's the second number. If I want to take the bitwise AND, then I just look at each number, each position, and AND those values between the two numbers. So 1 and 1 is 1. Yeah? Mm-hmm. 1 and 0 is 0. 0 and 1 is 0. 0 and 1 is 0. 1 and 0 is 0. 1 and 0 is 0. So I'm only going to have a 1 in a bitwise AND where both binary values have a 1 in that position. Does that make sense? I only get a 1 in the AND where both of the numbers have a 1 in that position. So that's only true in this first position. All the other positions, one of the other of them is 0. So I'm going to have zeros for the bitwise AND for all those other positions. Does that make sense? So if we take the same two numbers, but we do it with OR. Then we only have to have a 1 in one or the other in order to get a 1 in the bitwise OR. Yeah? So for these two numbers, there's at least one 1 in each position. Therefore, the result is all 1s. The way that we use this, the way that I've seen it used the most, is with permissioning or authorization for rules. Okay? So we'll, for example, have a string or an array of 0s and 1s where each position represents permission to do something. Okay? So like this user can modify this content, you know, or can add users, or can delete content, or whatever. Each one of these indicates a permission. And for a user, we would represent that the user has that permission by putting a 1 in that spot, and that they don't have that permission by putting a 0 in that spot. And then we can use a bitwise AND to determine if the user has that permission. So if we go back to this one, if I want it, say that this first position is this user can edit content on this page, and I wanted to check, I wanted to do an if to see if this user has permission to edit content on this page, then I would AND this user's whole permission string with a 1 in this position. And if I get back a 1, then that means they had permission to do this thing. If I get back a 0, it would be like this case. If I AND this one with a 1, I would get back a 0, which would tell me they don't have permission to do this thing. Okay, so that's the way I've seen it used in computing the most. Yeah.
So would each like number represent a different thing they would have or have not permission for?
That's right.
So like sending comments, editing comments, making comments.
Yes.
Photos, taking photos. And
Yeah.
it's like true, false, true, false, true, false.
Yes. Okay, so what about NOR? Do you remember what NOR is? Not OR. So if this was the result we had for OR, 1s all the way across, what would be the not OR? 0s all the way across. Okay, it's just the opposite. So we'd have 0s all the way across. Exclusive OR. So what was exclusive OR again?
Only if 1, not both.
1 but not both. So with the same numbers, it's almost like the OR, except in the case where they're both 1, we have a 0. In the place where it's only one or the other, we have a 1, it's a 1. Okay? Oh, let's fix that. Okay, now, so this is gets to your question, Glenn, when we've got 3 things that we're comparing. So first of all, what am I trying to find here? What does this say?
P or Q.
Not or.
Oh.
And, because this one looks like an A. That's how I remember. P and Q.
Or not P.
Or not P. And so what do I do first?
Checking if P and Q.
That's right, because that's in parentheses. So I do that first. So here's my truth table setup, which is always the same way. So P and Q, I do first. And what am I going to have here for P and Q?
True.
Yeah.
False, false.
Yeah. True, false, false, false. Does everybody get that? Okay, now I need to OR that with not P, right? So first I'm going to create a column for not P. So what would be in my not P column?
False, false, true, true.
Yes, so I look at my P column and I write the opposite in the not P column. So false, false, true, true. Oh, I went too far there. And then I do the OR. The OR. Okay, so I take this value, P and Q, and I OR it with not P. So So I have true or false. True. False or false. False. False or true. True. False or true. True. Yeah? So you just have to just take it one step at a time. All right? And this, we're doing it with symbols here, but when you will have if statements that get to be complex like this at times. And you should strive to not get too complex in your if statements, because you'll be confused about what you're actually checking, and people who look at your code and have to maintain it will also get confused about what you're actually checking, and when it evaluates to true and when it evaluates to false. Okay? But that's how this is useful. It's useful for constructing if statements where we're considering multiple different conditions, right? And the relationship between those conditions. And when do we want to do something? Okay, so let's look at some examples. If there's smoke, S, we're going to call that one S, then there's fire. We'll call that F. So what kind of a relationship is this? It's an implication. And what's the implication?
That if S is true, then F must be true.
Yeah, S implies F, right? So the implication looks like that. If we were using those symbols, S implies F. And in English, or if we wrote an if statement, we'd say if smoke, then fire. All right, what about the next one? If it is raining, we'll call that R, and I'm outside, we'll call that O, then I will have my umbrella. So there's a couple of things going on here. What are the couple of things going on? The first part, if it is raining and I'm outside, what is that?
And then an implication.
That's
Or is it
right.
an equality for the second one?
No, it's an implication. Yeah, it's an implication. If I said if and only if, then it would be an equality. But if is just an implication. So what would that look like in symbols?
R and O in parentheses
Yeah?
implies
Yeah. Don't need to put parentheses because there's only two things there. And we logically have to do those things to figure out the order of operations would dictate that we did the binary operation before we do the implication, but it wouldn't hurt to put parentheses. So, raining and I'm outside implies I'll have my umbrella. Okay? So in if terms, it would look like that. Okay, I will wear bunny ears on Twitch. We'll call that B. If I get another subscriber or a donation. So this one's a little bit tricky because I've written it in a way that it's sort of a little bit backwards. So what do we have here? Again, we have two things going on. What do we have?
Sure is what we have.
Union
Hey.
B, implication B, so S or D in brackets, implication B.
Yes. So we have a binary operation, an OR operation between subscriber and donation. So, and that, the result of that binary operation implies B. So if subscriber or donation, bunny ears. Okay? What about this last one? An admin, we'll call that A, or a teacher, we'll call that T. Staff has access, given that no staff is both a teacher and an admin. So they have access if they're not a teacher and an admin. That's right. That's an exclusive OR binary operation. And it implies access. Yeah. So A exclusive OR T implies access. And the way we would write this gets to be complicated in an if statement. If admin or teacher and not admin and teacher. That's another way to write exclusive OR. So one or the other and not both. Both of those things have to be true in order for exclusive OR to evaluate as true. Okay? Then has access. All right, that's it. See, that wasn't too bad, was it?
Is that all 41 slides?
No, this is the Boolean algebra. Our spec is 41 slides. We'll do that after lunch. Okay. Any questions about any of this?
Are we going to do an assessment on this besides
Oh, yeah.
just a test?
A
or is
test.
it actual- So not an assignment or anything?
Not an assignment because you use this in every piece of code that you write.
So we just have to give you all of our code.
Yeah, no. There's a discrete maths test. I'll give you. I've got a review. I don't want to give you the whole review because I don't want you to stress about stuff we haven't talked about yet. But I can give you the whole review if you want it, or I can give you like pieces of the sections of the review as we cover them.
Yeah,
What do you guys think would be better?
Yeah.
Yeah, like I don't mind if you do. I just don't want it to stress you out, right? I don't want you to get overwhelmed because some of the stuff we're going to go over gets a bit hairy. But and I don't want you to worry about that. We're going to, I'll take you through it. Okay. All right. So there is some Canvas content. There's and I did look through it this time to make sure there weren't mistakes. There's some really interesting examples in here.
Great pop culture.
Oh my gosh. I read through it. I was like, okay. Don't know if I would have chosen those exactly, but that's all right.
Oh, God.
Yeet.
Yeet.
Yeet
How old is
implies
this man?
he's not this young, but I think maybe he wants to be.
Who wrote it?
This is oh my God, his name just flew out of my head. We have more than one of them.
James, right?
Yes, James. Thank you.
Oh, James.
Yeah, not Lane, but
Oh, yeah.
yeah. If you want to be my lover, you got to get with my friends.
That's a
So
pretty old reference.
that's kind of
Well,
old.
you're lucky Scotty didn't write it.
Yeah,
Because
it'd be
otherwise
all Kanye.
it'll be about Kanye and Beyonce.
It would. It would.
That's one we
This one, I don't even understand this one. This is how old I am. I'm like, I don't even, are these words? What is, what is that? I don't understand that.
No, that's a dark corner that you don't need to understand.
Okay, good. Then I won't go there
Just
then.
listen to the song from beginning to end and you'll get it.
She's a Twitch streamer with a rather questionable past, and someone made a fake tweet from her
Oh, right.
where she accused an artist of being un-Muslim because she was smoking a certain product.
Right.
And then they made a diss track about her that became famous on music app
Okay.
called TikTok.
Yep.
Deep
Yeah.
reference.
See what I
Yeah.
mean?
Yeah, right.
It's
You'll
So-
know
To be quite frank, probably not appropriate. For
Yeah.
content.
Yeah. That's, I was wondering. I probably should have looked it up to see. I don't know what that means.
Yeah. Don't.
Okay.
Google it.
All right.
Don't Google it.
So here's some challenges. There's a Trump reference in here too. What? Okay. So here's some practice for you, and then here he is. That's James. So there you go. He's not that young, right? I mean, he's kind of young. He's pretty young. So you can watch his video explanation.
Very serious ethical questions about what's.
Okay. Yeah. All right. Now I will take that on. You can watch his video about the same content. He'll talk about it in a completely different way than I just talked about it. Okay. So, all right. So for the next till lunchtime, because I don't want to start the RSpec before lunchtime, but what I want you to do is to make sure that you follow the steps to be prepared, and if it doesn't work for you, to let me know so that we can get it working before we come back after lunch.